Okay, so the first one is hydrobromic acid. So hydro tells us what kind of acid? Binary, exactly. You're not going to be able to see any of these colors. That's okay. All right, so it's binary. So we're going to have our hydro. And then bromine is Br. Here, you know what? We can do this. I'll write it off to the side. There you go. Is that better? All right, so H, Br. That's it. Okay? Okay, nitrous acid. So when we see the aus, what does that tell me about that nit family? It says nitrite. All right, what is nitrite? NO2. What's the charge on nitrite? It's always a -1. Think about the word Nick in that one sentence, okay? Or Nick back there. All right. Okay, so this one is going to be HNO2. Okay, carbonic acid. So no hydro again. So who are we talking about? Carbonate, right? Carbonate, that's camel in the sentence, okay? So carbonate is CO3 with a what charge? -2. Camel, 2 vowels. Not for now. Yeah. There is really a difference, but don't worry about it right now. All right. All right. Phosphoric acid. Okay, phosphoric acid. So who are we dealing with? Phosphate. Not phosphorus, just phosphate. All right, so we have phosphate, which is phoenix from the sentence. So PO4, PH, and X. Okay, and then a -3. Good. All right. So with that, we're going to throw our H in front, crisscross, so we end up with H3PO4. And this last one, it starts with hydro, so what does that tell me? It's binary. All right, so we're just crisscrossing charges here. So we're going to put our H here, who's a plus. Tellurium is a 2-. We're going to crisscross. We got H2TE. TE, tellurium, number 52. Okay, all good? Erase it. Let's try the next one. You guys requested practice on this, so we're going to practice in the warm-ups, okay? All right. Okay, next one. Let me shrink it down so we're going to be right. Is HI. When would we ever have a lowercase l next to an H? Never. All right, so go ahead and name. Okay, so this first one we have HI. HI, is this binary or ternary? Binary, so what do we start with? Hydro. By the way, did you recognize these were all acids? That's actually the first thing you should have looked at, okay? You should be asking yourself, is there metal? And you kind of take yourself to both sides of that flow chart that I posted. And then you need to say, is that H kind of sticking in the front? That's usually your indication that you got an acid, okay? All right, so this one is hydro, iodic. Why are we ending with ic? Oh. Why do we end with ic? Do we ever end with anything else on a binary? There you go. All right, good. All right, so the next one, binary or ternary? Binary again. So we're going to say hydrochloric acid. You see that ic ending and the hydro beginning. Okay? All right, the next one, binary or ternary? Ternary. So we have to figure out first who SO3 2- is. This is sulfite. Okay? So in our, it's supposed to be an I. There we go. All right. It's not sulfite, it's sulfite. All right, so sulfate is in the sentence, which is supper, so that's SO4 with a 2-. Okay, so we take it one lower, we go to sulfite. Okay, so knowing that, we have ite. What's our ending? S. Good. So we're going to have sulfurous acid. Okay? Okay. Okay. Next one, we have HNO3, binary or ternary? Ternary again. So we're going to have to figure out who NO3, and it has a -1 charge, since there's nothing on my little nitrate. Good. So what do we end with? Nitric. Good. So this will be nitric acid. And if you're not knowing where we're getting the ick and the us from, remember, ick, I ate a humongous bite. All right? Link them up. All right. And then HiO4. Periodic, yep. All right. So IO3 is your iodate. There you go. And then IO4 is going to be your periodate. Okay? So we're going to have periodic acid. All right. Huh? Periodic acid. Periodically it happens once in a while. Okay. All right. All right. End with this one. Make it a good one. Thank you. For this all right, the first thing I want you guys to shout out is going to be whether it's ionic or molecular, okay? So for this first one, we had a what? This was an ionic, so I'm just going to put an I. All right, and we had who? Barium and iodine. So we're going to say barium iodide. Okay? Biggest mistake that I saw on the quiz is people wanted to put little oh, sorry. Actually don't know. Let me see. Is that better? Yeah. Okay, there you guys go. All right. All right, number 2. Molecular or ionic?
Or no.
This is molecular. There's 2 nonmetals here. Okay? So that means we use prefixes. And oh, this isn't the one that, there's one. Where did we all learn septa? Because I swear everyone put that on their quiz. Septoxide or something, or septa.
How many sides are on the shape?
7 is what? Hepta. Hepta, not septa. So get that out of your head. Okay? We're all clear? That was hilarious. Like, I was like, why? Why is there so many S's? It's never septa. It is hepta. 5 is penta. Yes. Okay. All right. So back to this one. We have, what's 4? Tetra.
Tetra phosphorus trisulfite.
Good. Tetra phosphorus trisulfite. Sulfide. Sorry. All right. Number 3.
Ionic.
This is ionic. All right. Perfect. Okay. I had a lot of people on the quiz say HO instead of O. Don't put HO. It's O for hydroxide. Okay? Okay. Yes. And make sure you always crisscross. All right. All right. Number 4, ionic or covalent? This is ionic. Good. So this is iron.
Carbonate.
It is not iron carbonate. It is what? Iron 2 carbonate. Why do we have to do that? Where is iron on my periodic table? It's a transition. So he's a multivalent guy. All right. How did we figure out it was 2? What's carbonate's charge? A -2. So if we reverse crisscross this, that's why there's no subscripts here. Okay. So iron 2 carbonate. All right. Number 5.
It's ionic, sodium dichromate.
Yep. Sodium dichromate. All right. Number 6. Molecular ionic. I can't speak. What is it?
Ionic.
It is not ionic. This is molecular. You have 2 nonmetals.
Oh, I'm looking at the wrong one.
All right, so diiodine pentoxide. Okay. Oh, that was another mistake. Make sure your second guy has the "ide" ending on it. Okay. Okay, there we go. All right, and then number 7, Ionic. This is copper.
2 perchlorate.
Yes. Yes, you're right. In my head, I had to spell out the word clam. Sorry, you're right. I know. All right.
Confuse me.
Clam, because clam has how many consonants?
3.
3. So that means chlorate with ClO3. So that's why I had to think about it for a second. All right. All right, number 8.
Molecular.
This is molecular. So we're going to say carbon. Good. And then finally, number 9. This is molecular as well. Diboron tetrachloride. Okay? Diboron. Just kidding. All right. Diboron. Okay. All right. Any major questions or anything that you saw up here today that is not matching up with something that maybe you were studying, or any questions, major questions? Did everyone kind of see how we kept using that sentence? Use those little mnemonics the best you can, and it helps you remember things in order to figure out extra little polyatomics, okay?
This helped a lot.
I hope so. All right. Okay. Percent composition, you need to know the different parts, right? And you're going to be using your periodic table a lot. Big thing to remember is those subscripts are counting how many of each atom you have. So you have 3 moles of nickel, basically. Don't forget, subscripts are also moles, okay? So we can say 3 times our nickel molar mass, okay? How many phosphorus do I have? How many moles of phosphorus? 2. Good. Remember that. 2 applies to everything inside. And then how many oxygens do I have? 8. Okay? So in the end, what you would be doing is you would have 3 times, I think nickel is 53-ish?
58.69.
Oh, okay. So 59-ish. Okay? You would have your 2 times, what's phosphorus?
30.97. So
31-ish?
yeah.
Okay, and then you would have 8 times 16-ish, okay? Once you've gotten those, you'll have a total, all right? Please know that your percent composition is going to be part over whole, and you usually push equals, and then times it by 100, okay? Okay? So part over whole times 100. So when I say part, you do have to make sure you're counting how many they have. So make sure you're counting for 3 nickels and 2 phosphoruses and 8 oxygen. Yes. Okay. I'm going to move to the bottom of the page very quickly. Empirical and molecular formula. All right, we're going to write down our steps for empirical formula. Okay, your empirical formula is the simple formula, which means everything should be reduced down. Okay, so when we're talking about these formulas, we're only talking about molecular compounds, right? Ionic should already be reduced all the way down. Molecular compounds, they can be whatever they are because we have prefixes to name them, right? So empirical formula will be the simple one. So when you have your empirical formula, most likely we give it to you in percentages. There'll be some times when we don't. But you want to make sure that percentage is no longer a percent. You just cross it out and you put a G there instead. So there is no moving the decimal, nothing like that. You just change them all to grams because you are assuming 100 gram sample. Okay? That's why we can do that. You're saying, if I had 100 grams, then this would be only, whatever, 4.07 grams of it. Okay? All right, once they're in grams, we need to get it to chemistry language. So we're going to convert grams to moles. The simple way to do that is divide by molar mass. Okay? Okay, the third step is once they're in moles, you're going to divide them all by the smallest. And then those are your subscripts, okay? Okay, before you guys take off, please write down this molecular formula as well. So for molecular formula, just know that you're going to have molecular formula mass divided by empirical formula mass, and that equals a ratio that you multiply by your subscripts, okay? And I'll continue this video. You guys need to watch it all the way through number 32, okay? So take notes. I'll keep it short, sweet, simple in the video, okay? I won't do them all. Let's go ahead and run through 28. I'm going to go ahead and do it together. I was going to have you guys do it on your own, but let's run through it real quick together, just to remind ourselves, make sure we know how we're doing empirical formula. So here, what's our first step? It's on the page before it if you need to look. You change it to grams. Why are we able to change all those percents to grams? You're assuming a 100-gram sample. Good. So we have 26.6 grams. And I'm going to divide it by what? It's going to be the molar mass. Good. Why am I dividing it by molar mass? To change it to moles. All right, so that's the second step, right? I'm just going to do each element individually. Is that cool? We're all understand. Okay. All right, so I'm going to take 26.6 grams. I'm going to divide it by the 39.10, okay, to get it into moles. All right, so this is 0.680 moles of potassium, okay? All right, we'll do the next one, 35.4 grams of chromium. We can divide it by its molar mass. I'm just trying to save you time here, which is 52 grams. And it equals pretty much the same thing. Okay. And then finally, the last one, which was 38.1%, we're going to say 38.1 grams of oxygen. I'm going to divide it by its molar mass to get 2.38 moles. Once we are here, who can tell me the next step? Good, divide by the smallest. So these guys are our smallest. We're going to divide both of them by that. I'm just going to go ahead and put 0.68 because that's pretty much what it is. Okay, and we'll see 1, 1, and 3.5. Yeah, so this is going to be KCrO 3.5. Yes. Totally. All right. So we gotta take care of that. What do we multiply everybody by? 2. Good. We're gonna multiply everybody by 2. So this is gonna change it to be K2CR2O7. You guys should be able to recognize this. Who is that? That's the dichromate. Okay, so that is potassium dichromate. I know we kind of rushed through molecular formula, so I'm just going to kind of run us through that one again. Who can raise their hand and tell me how we approach molecular formula? What does it all come down to? Starts with R, ends in atio. Yeah, it comes down to a ratio. Great. Okay, cool. So what it is you have your two masses. Okay. Okay, you have your two masses. So the molecular formula mass is the one that they tell you, right? So it's going to be 294.2. Empirical formula mass I have to find, right? So I take all of these and I figure out what empirical formula mass is. This time it happens to be the same exact thing. So what does that mean? This is its empirical formula and molecular formula. Now, if that had not worked out, if that came out to be like a 2, I would now multiply all of my subscripts by that 2. And that's the big idea here. Okay, so what it's looking like is, I'm going to go for one more minute. But you guys will most likely have to watch 30, 31, and 32 online tonight, okay?
Are the videos posted already?
Not yet. Okay, they will be there. All right, so 29 is about balancing, okay? When you go to balance things, I like to always draw a line down the middle, and I put my characters off on the side, and I see what numbers I have of each one, okay? So I have 2, this one I have 6, this one I have 3. Over here I have 1, 2, and 3, okay? And then you need to put in coefficients in order to balance. Yeah? So I would start with a 2 at here. You kind of want to leave your H's and O's for later, okay, for your last step, okay? And that's kind of it. Are you guys 11 or 10? 10, yeah. Clean up. You're good. Okay, so hopefully you try balancing this on your own. But what you would do is, now that I've put that 2 in front of the carbon dioxide, you're going to go ahead and rewrite this. So let's see here. So this side we're going to have 2 now. And then for oxygens we have 5. Okay? So looking at this, we want to, this is usually the easiest one to change. So let's go ahead and mess with our water over here, because I don't want to mess with my carbons anymore. So I'm going to go ahead and look at how I need to relate my hydrogens. So I'm going to put a 3 in front of this. What that does is that changes my hydrogen to be balanced. And then my oxygens are now 7. Okay? We have 1 extra here, so I need to get this whole thing to 6. So we're going to put a 3 here. And now we're at 7. Okay? When you are drawing the particulate diagram, you want to notice that this is a combustion reaction. Notice that your products have carbon dioxide and water. Okay? When you're drawing a particulate diagram, you have to show the 3 or the coefficients. Okay? And then carbon dioxide, if you remember. Okay? And then we can go backwards, and we have 3 diatomics of oxygen. And we have some C2H5OH. So that, I don't mind how you draw it. You're going to show 5, and then you usually have your OH tagged on. Okay? So looking at this, this is what you should have been doing. I maybe would have spread them out a little bit more to show the gas. All right, so let's look down at number 30 now. Ooh. Okay, so number 30 says, determine the amount of iodine produced when 145 grams of potassium iodide react with excess copper 2 chloride. So for this, we want to cue in on the whole idea that excess, we don't want to even worry about anything that is in excess. Therefore, we're just going to worry about the other reactant, which is potassium iodide. If we had another one, we would have to treat this like a limiting reactant problem, but we do not need to worry about that. So we have 145 grams of potassium iodide. And we need to relate it to iodine. So this over here, okay? So what we're going to start with is we're going to start with dividing by its molar mass, okay? And potassium iodide, if you look at your periodic table, should be about 166.01 grams, okay? And now I'm in the mole. So the next thing to do is bring words down to the right. Okay, if you notice, that's all that we're doing here. We're going to bring words down to the right, and we need to relate it now to iodine. Okay. When you're looking at that, you're going to look at your coefficients. So this would be 4 to 1. Okay. And then your last step, let me shrink this up just a little bit. Your last step is going to be bringing these words down to the right. So I'm going to say moles of iodine, and we want to get to grams. Okay, I know 1 mole of the diatomic is 253.82 grams. Using this, we're going to go ahead and say, we're going to multiply everybody at the top. So 145 times 1 times 1 times 253.82. You should push equal in your calculator. And then you're going to divide by 166.01. Push the divide again, 4, and push the divide again for 1. Hopefully after you have done that, your answer you should be seeing is 55.42 grams of iodine. So this is the start of stoichiometry, or start of our review of stoichiometry. You had some on the summer assignment. So just a quick reminder, you want to always hit this little mole bridge or this mole ratio. This is how you can relate things. Everything has to be in terms of the mole in order to do that. You cannot relate a gram to another gram without going through the moles. If you learned about Moletown and all that stuff, you want to travel from Gramland to Moletown, cross the bridge, and then come back to Gramland. Okay? If you don't know what that is, don't worry about it. I can load another video later, or I think it's on the summer assignment video. Okay? All right, that leads us to number 31. All right, so 31 is saying, it's talking about baking soda is often used as an antacid. It neutralizes excess hydrochloric acid secreted by the stomach. Okay, so then they're talking about milk of magnesia is also used as an antacid. It wants to know which is more effective antacid per gram. Okay, and so what you want to be thinking for this one is you want to relate it to how much is it going to react with the acid. Just like a neutralization, you want it to react with the acid. I also found that you can relate it to making the neutral water, but that's not the preferred route. Okay? All right, so what you would start with, we need to compare both of them. So I'm going to start with my baking soda, and I'm going to say 1 gram of this baking soda. And I'm actually, for easy purposes, I'm going to go ahead and say just baking soda, okay? All right. And then we're going to bring words down to the right. So I'm going to bring grams of baking soda. We need to get it into 1 mole. Okay, so looking at all of these, find them up on the periodic table, you would get a molar mass of 83.99 grams. Okay? And then I'm going to bring moles of baking soda down to the right. This is where we're going to relate it. This is my mole bridge or my mole ratio. I'm going to go to moles of hydrochloric acid that it reacts with. So when I look at this, we're looking at our coefficients for our ratio. They're both 1s. Okay? So you're going to type that in, and you're going to get an answer. I'm going to go ahead and let you take care of that. Okay, so hopefully you got 0.012 moles of H2O. I could have gone a little bit further and found out the grams, which would probably be more useful, but I'm going to go ahead and stop at moles. Just know that using its molar mass, we could have continued on. Then I'm going to compare it to the other one, which is 1 gram of milk of magnesia. So we'll put mm, okay? And I'm going to bring my words down to the right, okay? You need to go into moles, just like we did above, okay? We know 1 mole of this, looking at our periodic table, is going to be 58.3 grams. Okay, continuing on, we're bringing words down to the right. And we should be looking again at our coefficients. So I have a 1 for milk of magnesia and a 2 moles of hydrochloric acid. Okay, so again, we're trying to figure out how much of the hydrochloric acid it's reacting with. If we type this in, we end up finding out that it is 0.034 moles. So sorry, I put H2O there, of HCl that it's reacting with, okay? Looking at this, which one reacts with more? And your favored one is going to be that milk of magnesia because it is reacting with more hydrochloric acid. Okay, that moves us to our last one that I need you to have recorded before tomorrow. And that is that an industrial method for production of elemental zinc from its ore to roast the crude ore in oxygen and then react it with carbon monoxide. The following reactions describe the chemical process. Okay, so then they tell us that we have a 10 kilogram sample of an ore containing zinc sulfide, which was chemically treated according to the reactions described above, producing 2.85 kilograms of zinc. Determine your percentage of zinc sulfide contained in the original sample of ore. Whoa, lots of stuff here. So what we're imagining here is that you have a whole thing of this ore, and we just want to know how much is going to be this zinc sulfide found inside of it, okay? So if we are looking for our zinc sulfide, okay, you can kind of see that we have to, they're starting us with 2.85 kilograms, which is, by the way, 2,850 grams, okay? We need to get up here, and they want us to start down here. So what you're going to do is we're going to do stoichiometry to this side. If you notice, zinc oxide appears in both of these. That's our connecting route, okay? Once we get to this, now we can stoichiometry over to zinc sulfide to find out what we need to find out, okay? So we're going to start with the 2,850 grams of zinc, okay? I'm going to bring the words down to the right. And we know that 1 mole of zinc is 65.41 grams. That's its molar mass, okay? And that's equal to 1 mole of zinc. Then I'm going to bring those words down to the right, and I have moles of zinc. Remember, we're now going to relate to zinc oxide. So this is my mole bridge, or my mole ratio. It's a 1-to-1 ratio we end up finding out. Let me actually do this in a different color. Okay. Now we're going to bring those words down to the right. Okay. And we are now relating it to the one that is above. So we know that for every 1 mole of this compound in the second part, it's coming from 2 above. Therefore, we're going to say, we're going to go with the one that's up here because we now want to relate it to zinc sulfide. So we're going to say 2 moles of zinc oxide for 2 moles of zinc sulfide. And we do have to take it that extra step to find mass because of what they're asking us for. So we're going to take that 1 mole of zinc sulfide, and we're going to have our molar mass of 97.44 grams. Again, that's coming from my periodic table, okay? If we type this all in, okay, so we're multiplying everything on the top and then dividing it by everything on the bottom, okay? When we do that, we are going to end up getting 4,250 grams of zinc sulfide. So back to the original question, they want to know the percentage of zinc sulfide contained in the original sample. Well, they tell us at the beginning that the original sample